Asia. If you missed the first workshop 2 weeks ago, you can watch the recorded video on YouTube. So please search the keyword Avalanche Hackathon Asia. And in that workshop, also hosted by me and my colleague Wilson, we spoke the reason why we're having this hackathon and a brief introduction of Avalanche, the blockchain. However, due to the limitation of time, we did not cover details, but today I'm honored to bring two talented developers from the headquarters Avalanche, who are Laine, our senior software engineer, and Gabriel, developer evangelist. And personally, I think Gabriel is a man full of passion. So these two gentlemen today will speak about more details of Avalanche. In Dan's part, he will introduce the consensus, which is called Snowball. So Snowball consensus is very unique, unlike the Bitcoin or the Ethereum consensus you might be familiar with. Also, Dan will speak about the Validator and Subnets, which are two quite important elements in the Avalanche system. Finally, Dan will tell us something about how exactly the transaction works on Avalanche C chain. Okay, so let's get started and bring Dan first. Please, Dan.
So random noise in the network because of the random sampling yields some increased network preference for one choice, which begets more increased network preference for that choice until it becomes irreversible, and then the nodes can decide. Okay, so Snowball generalizes to multi-value decisions, not just binary ones, right? Like we had pizza or barbecue, that was a binary choice, or blue or orange. But it turns out that actually this generalizes to multi-value decisions where you can be deciding from not just two things, but many things. So one thing to note is that the liveness and safety thresholds of this algorithm are actually parameterizable based on the parameters that you give it. So as you increase the quorum size, this parameter alpha, the safety threshold increases and the liveness threshold decreases. So what that means is the network can tolerate more Byzantine nodes and remain safe, safe being all eventually agree on whether something is accepted or not. And as you increase beta, the number of consecutive successes that you need before accepting something, as that increases, the safety threshold increases and the liveness threshold decreases. The liveness threshold is the amount of malicious participants that can be tolerated and still make progress towards making a decision. So these numbers are constants, and they're actually pretty small. So on the Avalanche network right now, the value for K, the sample size, so when you ask a group of nodes what their opinion is, you only sample 20 of them. The quorum size is 14. So if 14 or more give you the same response, then you adopt that as your preference. And the decision threshold is 20. So you need 20 consecutive responses the same way in order to decide on something. So something that's really cool, and that I'll come back to, is that this is super scalable as the number of nodes in the network increases. That's actually pretty cool, because regardless of the number of participants in the network, the number of consensus messages that you need to send stays the same, right? Because you're only going to query at a time 20 nodes. So it doesn't matter if there's 20 nodes in the network or 2,000 nodes in the network, you're going to send the same number of messages. So I'm going to introduce a data structure called a DAG, or a directed acyclic graph. And you all might be familiar with these, but I'm going to go through a little bit of stuff about them just for completeness. So a DAG gives a partial ordering of things, right? So in this example, A is before B because there's a line from A to B. B is before D because there's a line from B to D, and similarly, D is before E. So transitively, we can say that A comes before E, but this is a partial ordering. And what that means is that for some things, the ordering is not defined, right? Like B is after A and C is after A, but there's no notion of whether B is before or after C. Okay, and two other pieces of terminology that I want to introduce are ancestors and descendants. So ancestors is basically everybody that you can draw a line up to in the graph. So the ancestors of D, for example, are A, B, and C. And the ancestors of E are, you guessed it, A, B, C, and D, because you can draw a line backwards to any of those. And the descendants are the opposite of your ancestors. So the descendants of A are B, C, D, E, and we're going to see why that's important in a minute. So Avalanche uses a DAG to store things as opposed to a linear chain, right? Like Bitcoin or Ethereum, there is a chain where everything has one parent and one descendant, and Avalanche has a DAG, which means that something in the DAG can have multiple parents. So a common source of confusion is the parent-child relationship in the DAG does not necessarily imply an application level dependency. This is just something that we kind of use to move things along in consensus. So for example, just because B is the child of A does not mean that B's linked to A in the application. Like for example, if this is a peer-to-peer payment system, B doesn't necessarily spend a UTXO created in A or anything of that sort. Okay, so with consensus protocols, the name of the game is to prevent bad things from happening and to make progress when bad things aren't happening, or to just make progress, period, I guess. So we want to prevent the inclusion of conflicting transactions in the DAG, and conflicts are application defined, right? So like different applications will have a different notion of what it means for two transactions to conflict. In a peer-to-peer payment system, for example, which is obviously very big in the crypto world, for example, two transactions that try to consume the same UTXO are defined as conflicting. So in Avalanche, we have this notion of a conflict set, and transactions conflict set is, as you might guess, the transactions that conflict with it, right? Only one transaction in a conflict set can be accepted, or else your protocol is broken. Okay, so let's see how Avalanche works. So suppose that we've got this Avalanche network running and the sample size is 4, the quorum size is 3, right? This is the alpha majority response that we need, and beta, the number of consecutive successes that we need, is 4. So here's some happy node here, and he finds out about a new transaction called Y, and it queries the network, right? It picks K validators, and it says, do you prefer this transaction? And we'll get to that in a second, what preferences. And it gets its responses, and 3 of them say, yes, I prefer this transaction, and 1 of them says, no, I don't prefer that transaction, right? So alpha is 3. So we have an alpha majority because we have greater than or equal to 3 yes responses. So now we're going to update the DAG, which is this data structure that we have locally. And I know there's a lot here, but I'll break it down. So if you get an alpha majority yes response for a transaction, you give that transaction what we call a chit. A chit is just a Boolean or a 1 or a 0, if you want to think of it that way, that says, when I queried the network about this transaction, an alpha majority said that they preferred it. So transaction Y here, we give it a chit. And there's also this notion of confidence. And confidence is the sum of your chit, 1 if you got a chit or 0 if you didn't, plus the sum of all your descendants' chits. So let's look at this graph. So transaction V got a chit, and it has 3 children, or 3 descendants, I should say, that got chits. So its confidence is increased from 3 to 4. Similarly, for transactions W and X, they both have a chit, and they both have a descendant with a chit, so each of them have confidence 2, and transaction Y has confidence 1. And we also have this consecutive successes counter, which is, well, I suppose we'll see that in a second, but it's the same notion as in Snowball. The number of times that this transaction or a descendant of this transaction received a successful alpha majority query, right? So before, transaction V had 3 consecutive successes, right? Itself and its 2 children. And now it has 4 consecutive successes with transaction Y, and similar for W and X. So the algorithm this node follows is it got an alpha majority response of yes votes. So it gave transaction Y a chit. It incremented the confidences of its ancestors, and it incremented the consecutive successes counter of its ancestors. Cool. So now, remember that we had beta, the number of consecutive successes required for a decision. We had that set to 4, and now transaction V has 4 consecutive successes, so it's accepted. Okay, so now let's say our node learns about some transaction Y prime, which conflicts with transaction Y. And we do the same thing as before. We randomly subsample 4 validators on the network, and we ask them if they prefer transaction Y prime. And in this case, 2 of them say, yes, I prefer Y prime, and 2 of them say, no, I don't prefer Y prime. Right? So this time we didn't get the alpha majority response. So what do? We update our DAG accordingly. So transaction Y and Y prime are in a conflict set, right? We said that they conflict with each other. Only one of them can be accepted. So we're going to say transaction Y does not get a chit because it didn't get an alpha majority response. It has confidence 0 because it doesn't have a chit and it has no descendants with chits. It has 0 consecutive successes because that query that we just did for it didn't yield an alpha majority response. And then we update all of our processing ancestors, which in this case is just transaction W. So its consecutive successes goes from 2 to 0. The confidence is still 2. This is an error. It shouldn't be struck through. So the use of confidence is when a node queries you and says, do you prefer this transaction? You respond that you prefer it if there's no other transaction in the conflict set with a higher confidence. So let me break that down for a second. So in this conflict set, transaction Y and transaction Y prime, transaction Y has confidence 1 and transaction Y prime has confidence 0. So we prefer transaction Y to transaction Y prime. So if somebody asks us, hey, do you prefer transaction Y? We'll say yes. If somebody says, do you prefer transaction Y prime? We will say no. Okay. So let's keep going. There's some new transaction Z, and we do the same thing as before. We query K validators, and we get a response. In this case, again, it's an alpha majority response because we get 3 yeses. So we update the DAG, and it gets a chit. It has confidence of 1. It has 1 consecutive success, and we update the processing ancestors. And in this case, the ancestors still don't have 4 or more or 4 consecutive successes, so nobody can get accepted yet. Okay, so that's really the gist of the Avalanche consensus protocol in action, but obviously there's still a lot left undiscussed. And here is what I was saying before, where if someone asks us if we prefer transaction Y prime, we'll say no, because we prefer transaction Y, which has a higher confidence. We prefer the one with higher confidence within a conflict set. So in practice, so first, what I discussed just now is how Avalanche consensus is described in the white paper. But at Avalabs, the implementation that we've done is a little bit different. We've made some optimizations for latency and throughput. And the most important of those optimizations, maybe, is that we have this notion of vertices. So it would be kind of a lot of overhead if every transaction, if we had to vote on every single transaction at once. So we batch transactions into vertices, and vertices are basically just batches of transactions. They act pretty much the same way that transactions do in what I've just shown you. If you receive a vote for a vertex, that is a vote for all of the transactions in that vertex, and votes are applied transitively upward, right? That's like increasing your ancestors' confidence and consecutive successes upon success. So the same principles apply. And we say that a vertex gets accepted when all of the transactions in it are accepted. If a vertex contains a rejected transaction, then that vertex gets rejected. So the first line is a restatement of what I've just said. So if a vertex gets rejected, all of its descendants get rejected too. And we kind of just ignore that part of the DAG and we cease to build on it. So rejected vertices, valid transactions. So if a vertex gets rejected but has valid transactions in it, we're just going to take those valid transactions and we're going to reissue them into a new vertex, which is not the child of a rejected vertex, and continue on from there. So Avalanche consensus is probabilistic in the sense that technically you're not guaranteed safety, but you are to an arbitrarily high threshold, an arbitrarily high probability of safety. But it is final. Again, I guess technically it is probabilistically final, but basically the gist of our safety guarantee is that if any correct node accepts a vertex, then all correct nodes will eventually accept that vertex, right? If one person decides pizza, then everybody eventually will decide pizza, all of the correct nodes anyway. Similarly, if any correct node rejects a vertex, then everybody will eventually reject that vertex. And this is final and irreversible. Once something has been accepted by a correct node, you are darn sure that it is accepted by everybody else too, and that will never ever change. So this isn't like Nakamoto consensus or proof of work consensus, where you know, there's your block might be included on the chain, but then later it gets reorged and then it's not part of the chain, and you have to wait like an hour or something for your transaction to have gone through and for you to be confident that it actually is part of the history. With this, the decision is final and it works really quickly. This happens in like less than a few seconds. So there's a few other optimizations that we do. You might have thought like it's kind of weird that we just ask, do you prefer this, yes or no, and everybody responds with a binary yes or no. That's not as efficient as it could be. So what we do is instead of asking, do you prefer this vertex, nodes say, hey, I learned about this vertex. So given that that vertex exists, which vertices do you prefer? And instead of just getting a binary yes, no back, you get what they think the accepted vertices will end up being, which helps you make progress faster. Similarly, the protocol, as I described it before, you only query upon hearing about a new transaction, but obviously you need a bunch of stuff to be happening on the network to make any progress, because you only make progress when there's a new transaction. So we don't do that, and instead the nodes just repeatedly query the network and follow that algorithm until there's no virtuous vertices processing. A virtuous vertex is one that doesn't have conflicts. If we allowed, if we had it so that we continued until there were no processing vertices at all, then that wouldn't be good, because you could just create, you could create conflicting vertices and have the network just churn forever trying to reach consensus on them. A final optimization is that nodes don't necessarily need to wait until they get all K query responses before registering the outcome of a poll, because sometimes you can tell that nothing is going to get an alpha majority. So at that point, you don't need to wait for the rest of the responses. You can just say nobody got alpha majority votes, reset all the confidences, etc., or reset all the consecutive success counters. So this is a proof of stake based system. So we don't use Nakamoto consensus. We don't use proof of work. So in a world where it's free to become a validator that's part of this network, then that's problematic because you can just start up like a billion nodes. Your nodes get queried all the time, and you as a malicious person can have those nodes do whatever you want and violate the safety and liveness threshold, right? So the validators, the nodes that are being queried as part of consensus, they have influence over the network and they have to pay for that influence. So basically we're tying real world value to influence over the network to prevent vote stuffing, to make sure that no one could just start up a billion nodes and, you know, break our system. So in order to make your node a validator, you have to bond or stake something valuable. And in the case of Avalanche, that's our native token Avox. The more Avox that a node bonds, the more often it's queried by other nodes, right? So it's not a uniformly random decision when you're sampling the network, right? So you have to pick K people to sample. You don't pick uniformly randomly. You do weighting based on the amount of Avox that they've staked. So if you stake more Avox, you get queried more often, you have more influence over the network. And we incentivize nodes to be validators by giving them a reward if, while they're validating, they're sufficiently correct and responsive, right? So we reward them for good behavior. And something else to note about Avalanche is that we don't have slashing. So if a node does not behave well while it's validating, maybe it gives incorrect responses, or maybe it just doesn't respond at all, then we don't burn their stake or anything like that or reduce it. We just give it back to them, but with no reward. So this is nice in case, I don't know, your node is down because AWS had an outage or something. So as long as a sufficient portion of the bonded Avox is held by correct nodes, then the network is live for virtuous transactions and the network is safe, meaning that, again, any correct nodes will agree on what has been accepted and rejected. So zooming out a little bit, I want to just hit on two big ideas of Avalanche consensus. The first one is the use of subsampling. So the fact that we do subsampling is really cool for the reasoning that I laid out before, which is that it has really low message overhead. So again, it doesn't matter if there's 20 validators or 2,000 validators, the number of consensus messages that a given node needs to send remains constant, which is really nice. It really allows you to build a decentralized system. And the second big idea is transitive voting, right? This idea that a vote for a transaction is a vote for all of its ancestors. And that really helps us make progress. That really helps with transaction throughput, because you're essentially getting a bunch of votes for one, right? So for example, in the diagram on the right here, if you get a vote for transaction D, then that implies a vote for all of its ancestors. So even though you just received a vote for D, that also counts as a vote in favor of A, B, and C. So this helps with transaction throughput because you're getting a lot of votes for the price of one, essentially. And with consensus protocols, the thing that a lot of protocols get hung up on is the number of messages that need to be sent back and forth becomes overwhelming as the number of transactions increases. And this helps to keep that down, because even if there's a lot of transactions being processed, you don't need to do a round of voting for each of them. You can just do votes on their children, and that is applied transitively upward. A few other loose ends to wrap up. How are transactions created? Good question. So users cause transactions to be created either by issuing an API call to a node, or just issuing a send or an issue transaction call to a node. Maybe if you've created the transaction manually using our JavaScript library or something, for example. How are vertices created? So nodes will batch the incoming user transactions into a vertex and query the network about it, and it'll get added to the DAG that way. Or, and this isn't written here, but again, vertices can be created if a rejected transaction has or a rejected vertex has valid transactions within it. Those will be regrouped into a new vertex and issued. And another loose end is how are a vertex's parents chosen? When a node is issuing a vertex, it'll just choose a handful of parents. This is a parameter of the system. It'll choose some number of parents from the virtuous frontier, and this is nodes that are at the tip, the end of the DAG that don't have conflicts, right? This is important, that we want to build upon virtuous vertices, because if we build on non-virtuous vertices, vertices with conflicts, then there's a higher chance that that vertex gets rejected and all the ones underneath it get rejected, and then we make less progress, and that's bad. So we only build on virtuous vertices. Just some other observations about Avalanche is that conflicting transactions are not guaranteed to be live, right? You might not be able to make progress on conflicting transactions, but that's actually not really a problem, because if you don't want your transaction to not be live, then just don't issue a conflicting transaction. So it's pretty much as easy as that. You only have to be worried about your transaction not going through if it has a conflict. And if it has a conflict, then that means that you presumably issue that conflict, right? So like, I can't issue a conflict with somebody else's spend transaction unless I have their private key and I can be spending the same UTXO as them. Another observation is that Avalanche works for linear chains too, right? You just do almost the exact same thing as before, except you restrict that a vertex only has one parent. So Avalanche is kind of more general than this, but you can restrict that vertices only have one parent, and that gives you a total ordering of vertices, or blocks if you want to call them at that point. You get a linear chain out of it, and that can be nice for certain applications. If you want to know, like, this came before this for every pair of transactions. Another cool thing about this system is that if there's no work to be done, then nothing is happening. You don't need to send consensus messages back and forth. You're not like churning, trying to add length to the network or anything, or to the chain. You're just sitting there kind of twiddling your thumbs, chilling out. And that's good, because proof of work does not have this feature. You constantly have to be doing work. That's a feature, not a bug, of proof of work. And that's obviously really bad from a sustainability point of view. And Avalanche solves for this. And finally, there's no leader. Anyone can propose a vertex. Anyone that has staked a Vox can vote on vertices. So there's no leader, which helps make the network more robust and decentralized. So kind of wrapping up and zooming out even more, why should we care about this? So Avalanche is a general consensus engine. What I've laid out, it doesn't really matter what kind of application you're putting on top of it. This protocol allows you to decouple state management, right? The like actual application layer of what you're doing from the consensus layer. So if you're building an application on top of this, you just have to define some notion of, you know, here's what conflicts mean. here's what a vertex, or here's what a transaction is, and so forth. And you don't have to worry at all about what's underneath. You just kind of have this black box that is the consensus protocol, where you put something into it and eventually it comes out as being accepted or rejected, and then you can move on from there. So you can use Avalanche for all sorts of applications, not just peer-to-peer payments, but for example, on the Avalanche network, we have an EVM instance running, right? It's your same favorite Ethereum virtual machine with smart contracts and Solidity and all of that good stuff. And underneath, we've basically just taken out Ethereum's proof of work consensus mechanism and plugged in our own Avalanche consensus protocol, which allows for lower latency, right? Just a few seconds between blocks, higher throughput, all that good stuff.
Okay, thanks for Dan's introduction. Okay, I guess there might be a lot of interesting stuff there, and you may need some time to read more materials and documents or watch this video again to understand the amazing parts in Avalanche. And if you cannot wait to get started and try to build something on Avalanche, the next speaker, Gabriel Cardano, will give you the necessary assistances like dev environment setup and toolkit libraries that you definitely will use in your work. So let's welcome our next speaker, the developer evangelist, the expert, Gabriel.
Hello, everybody. This is Gabriel Cardona, developer evangelist from Labs. And today we are going to be giving a high-level overview of the Avalanche Developer Toolkit. And this will include different services or libraries which are available to you as a developer in the developer Avalanche ecosystem. So brief introduction, who am I? My name is Gabriel Cardona. As I mentioned, I'm developer evangelist from Labs, and it is my incredibly cool and fortunate job to go around to different hackathons and meetups and conferences and conventions and to give presentations hoping to inspire people to build amazing dApps on the Avalanche network. And why do I do this? Because I believe that the most valuable asset on the planet at the moment is a competent, hardworking, and creative developer. And I believe that if you zoom out and take the 10,000-foot view of where we are in the evolution of our species, I would say we're just at the very beginning of seeing the glimmer and the promise of the potential of humanity. However, we have big problems that we need to solve at scale and velocity. Fortunately for us, there have been so many paradigm shifts in computer science going back the last 150 or 200 years, going all the way back to Ada Lovelace and Charles Babbage with the difference in the analytical engines, all the way through today, we have had so many paradigm shifts that we have a toolkit which is unlike any time in all of human history. So now we just need competent, creative, and hardworking people to step forward and build the systems which solve the problems. And I always say this, there's never been a greater time in all of human history to have a big idea, find a like-minded group of people, raise capital, launch a game-changing dApp, change the world, and make a fortune. And the amount of capital, both human and financial capital, required to launch a startup has been rapidly decreasing over the last couple of decades. And so, what 10 years ago may have cost $1 million to launch, and what 5 years ago may have cost $100,000 to launch, you can now launch for tens of thousands of dollars. And it's really because the software stack and the APIs are so powerful and the economy of expression is so great that it just simply requires less engineers to write and maintain the systems. In addition to that, nearly all of the platforms that you'll be using are either open source or they have a free tier, which brings down the cost of shipping an MVP. And then additionally, Web3 has value as a native primitive. So raising capital via ICOs or yield farming is what is popular and in vogue today. And in addition to that, there are many successful entrepreneurs from the blockchain space who are looking to put their capital to work for them. And so the story I like to tell to really bring home this point is that in 2012, when I was at Trulia, we did an initial public offering. We went public on the New York Stock Exchange, and our CEO, Pete Flint, had to do a roadshow where he traveled across the United States to many different cities, a couple handfuls, and he had to, meet with all the bigwigs and press the flesh and wine and dine everybody to get them to potentially invest in the IPO. And we had to hire an entire team of lawyers, and the entire process was very expensive and took 13 months or so to complete. It was pretty much wrapped in red tape. When we went public, Pete got to ring the bell on the New York Stock Exchange, and we raised $102 million in that IPO. Now, if you compare that with creating a token on the C chain and launching an ICO or an IDO, you can raise $100 million in one afternoon. And so the pace at which capital moves in Web3 is really shocking. And then lastly, everyone around the planet is just incredibly wired in right now, and ideas spread globally nearly instantly. So the amount of time between the introduction of a new technology and when it goes mainstream is decreasing. And so we should continue to see amazing ideas catch on like wildfire and spread globally. So now I want to talk about the actual different tooling in the Avalanche developer ecosystem. And we're going to start with Avalanche Go. So Avalanche Go is the reference implementation of an Avalanche full node. And as you can tell from the name, of course, it's written in Golang, and it contains the full breadth of functionality available on the Avalanche platform. So this includes the primary subnet, which consists of the XP and C chains, and a JSON RPC for each chain. So you can create variable and fixed cap assets. You can create non-fungible tokens. You can state AVAX as a validator or a delegator. You can create new subnets, add validators to your subnet, instantiate VMs as blockchains on your subnet. You can even swap assets back and forth between the different chains, the XP and C chain. There's also a key store API, which enables you to store your keys on the full node. However, we consider this to be an anti-pattern, and we recommend that you create and sign transactions locally using a tool such as Avalanche.js. And if you check out your home directory, tilde, there's a hidden directory .avalanche.go. Within you will find a staking directory. And in that staking directory, you will see both a TLS certificate and a private key. Avalanche uses transport layer security, or TLS, to protect node-to-node communication from eavesdroppers. TLS combines the practicality of public key cryptography with the efficiency of symmetric key cryptography, which has resulted in TLS becoming the standard for internet communication. And whereas most classical consensus protocols employ public key cryptography to prove receipt of messages to third parties, the novel Snow consensus family does not require such proofs. This enables Avalanche to employ TLS in authenticating stakers and eliminates the need for costly public key cryptography for signing networks. So we have TLS certificates. Avalanche does not rely on any centralized third parties, and in particular, it does not use certificates issued by third-party authenticators. All certificates used within the network layer to identify endpoints are self-signed, thus creating a self-sovereign identity layer. No third parties are ever involved. We also have TLS addresses. To avoid posting the full TLS certificate to the platform chain, the certificate is first hashed. For consistency, Avalanche employs the same hashing mechanism for the TLS certificates as is used in Bitcoin. Namely, the DER representation of the certificate is hashed with SHA-256, and the result is then hashed with RIPE-MD160 to yield a 20-byte identifier for stakers. And this 20-byte identifier is represented by the string node ID dash, followed by the data's CB58 encoded string. And CB58 is very similar to base 58 check. If you're familiar with that, base 58 check is a base 58 encoding with a checksum. So is CB58. The differences between CB58 and base 58 check are, with CB58, we only SHA-256 one time instead of twice. And we use the first 4 bytes of the, we've used the first 4 bytes as the checksum as opposed to the last 4 bytes. So if you see CB58 in our documentation, that's just a base 58 encoding with a checksum. It should be familiar to you if you're familiar with base 58 check. And of course, currently Avalanche Go is the only full node implementation on the Avalanche network. However, our intention is for there to be a rich and diverse ecosystem of full nodes. And of course, the analogy that I like to use is with the web and different web browsers. So, in the past, before the modern web, we had Internet Explorer and Netscape Navigator, and there were no web standards, and all of the functionality was reverse engineered by the different clients. And it was really quite a mess where web developers had to basically suss out the user agent string to figure out what browser they were serving up the app to. And then they would have to put big if-else statements serving up different content to different browsers. And they would even have a little banner at the top or bottom of the browser of the web page that said, this page works best with Netscape Navigator or Internet Explorer. And if you compare that to the modern web, where we have the World Wide Web Consortium and the HTML5 working group and CSS and ECMAScript and the DOM API, everything is very much spec'd out and standardized. And now we have all the major browser vendors, Safari, Internet Explorer, and Edge, Firefox, Chrome, Opera, etc. And they're all able to implement an app, and it runs the same across all browsers, just like Java's promise was to write once, run anywhere. That really came to fruition with JavaScript. But then the different browser vendors can add their own special sauce with regards to user experience. And we would like to see the same thing with full nodes in the Avalanche network. We would like to see multiple different full nodes written in different languages, which all implement some type of formal spec and then help suss out the edge cases and the bugs in the specification. Next, we have the local network runner. For firing up a local test or private network for development, this is akin to Ganache from Ethereum. We have what's called the local network runner, which is a tool to run and interact with an Avalanche network. But what about Avalanche, I may hear you say? Yes, that is very perceptive of you. Avalanche has officially been sunset, and the LNR is the LNR, which is what I'm calling the local network runner, is the path forward. And, you know, Avalanche was created before mainnet, and it was originally architected by an intern who, to be fair, was an amazing engineer, but he's since moved on. But just so much has changed since we went live with the mainnet. It's been such a journey that we've been talking about rewriting Avalanche from scratch, and this is the outcome of that. It's called the local network runner. Similar to Avalanche, the LNR is a tool to run and interact with the Avalanche network. The nodes that compose the network can run either locally or in a Kubernetes cluster. When you run it locally, each node runs in a process on your computer. In Kubernetes, each node runs in a Kubernetes pod, and the Kubernetes pods can be on your computer or remote. Regarding configuration, using the LNR, when you create a network, you specify the configurations of the nodes that are in the network upon creation. And so not only properties such as the node's name and the staking cert and key are configurable, but also configuration which is specific to the type of network runner being used. For example, a node running in a Kubernetes cluster has a config field that specifies the Docker image that the node runs, whereas a node running locally has a config field that specifies the path of the binary that the node runs on, or that the node runs. You can create a custom genesis, enabling creation of balances and airdrops and reward addresses. And there's even a default network creation. The local network runner implementation includes a predefined configuration, which allows you to create a new network without needing to define any configurations. And this is how you can quickly spin up a 5-node staking network with a pre-funded well address, similar to what you may have been doing previously with Avalanche. Also, the LNR lets you interact at the network and the node level. So you can start and stop networks. You can get their health, add and remove nodes, get node names. You can also drill down to a specific node to get its node ID and name. And you can even get a client for making API calls to individual nodes. And as an example of how to use the LNR, we've included a main.go file that uses the local implementation of the network runner. And when you run it, it creates a local 5-node Avalanche network and waits for all the nodes to become healthy. It prints the names of all the nodes. It prints the node ID of an individual node. It starts a new node. It removes one of the original 5 that it spun up, and then it replaces that with the new one that it just spun up. And this network will just run until you provide a SIGINT or a SIG-term. So as I mentioned, this is similar to the 5-node network that you might have been running in Avalanche. Similar functionality exists in the LNR. Next, we have the Postman collection. So Postman is a platform for building and using APIs. It simplifies each step of the API lifecycle and streamlines collaboration so you can create better APIs faster. If you're building REST APIs and you're not using Postman in your workflow, then I highly, highly suggest that you spend the time required to on-ramp your skills into Postman. It doesn't take long. It'll maybe take an afternoon. And Postman has a lot of great functionality. You can set environment variables, so you can use basically like variables across your different collections and requests, so you don't have to always define certain things like the different protocol, HTTP or HTTPS or ports or URLs, anything. You can create environment variables. You can have code snippets, so it will actually show you the curl request that you can copy and paste into your terminal. It has documentation, including links out to, you can link to your official documentation. You can change the different request and response types, so you don't have to do only post. You can do gets or puts or patches or any of the different HTTP verbs. And you can also get back the response status, the time, and the size. So this is incredibly valuable. We have a Postman collection. It stays at parity with the Avalanche Go client. Next, we have docs. So of course, we realize that the canonical answer to any question regarding how Avalanche works is always going to be read the manual, right? So with that in mind, we have exhaustive and up-to-date documentation. Of course, it is open source and it's written in Markdown. So we encourage even everybody at Ava Labs to contribute, even not engineers. So, we encourage everybody in our team to fork the repo. Anybody can pick up Markdown over the course of, an hour or less, and then to make the changes. And, this is a living document, and it is the canonical source of truth for our entire ecosystem. And we want to keep this up to date. So if you see something which is out of date or could be improved, we ask you to please fork the repo, make the change, and create the pull request. Updating docs remains the single easiest way to contribute to an open source project. It's a great way to connect with the team and help move the project forward while also building social equity. So again, if you see something that needs to be changed, we absolutely encourage you to reach out and make the change. Next, we have Avalanche JS, which is of course near and dear to my heart because it's the library that I personally maintain. And it is a TypeScript library for interfacing with the Avalanche platform. And it is, of course, built using TypeScript, and I'm a huge advocate of TypeScript. If the web touches your workflow, and I suspect that the web touches nearly everyone's workflow, then you absolutely must take the time to on-ramp your skills from JavaScript to TypeScript. You can really think about TypeScript like JavaScript 2.0. It was created by Microsoft with the intention of writing JavaScript in the large. And today, even writing Hello World, if you could see the entire stack trace, it's, hundreds of thousands, if not millions of lines. We are all programming absolutely in the large. And so the tooling that TypeScript provides you allows you to think of your abstractions so much more clearly, and you can express yourself, and then your abstractions will not buckle under their own weight. And so absolutely, in the same way I encourage you to on-ramp your knowledge into Postman, I absolutely encourage you to on-ramp your knowledge into Avalanche JS. The Avalanche JS library has the full functionality of the Avalanche library, so you can do everything that you can do on the X, P, or C chains, including creating variable and fixed cap assets, creating non-fungible tokens, delegating, validating, spinning up subnets, launching virtual machines, doing cross-chain swaps. Everything is available from Avalanche JS. Next, we have the Wallet SDK. The Wallet SDK is also a TypeScript library for creating and managing non-custodial wallets on the Avalanche network. It provides high-level methods for transacting on the X, the P, and the C chain, and it supports 4 different types of wallets. There's the singleton wallet, which is just a single SecP 256K1 ECDSA key pair. There's ledger wallets, so you can actually use the ledger hardware wallet. There are mnemonic or HD wallets, so basically you can encapsulate a source of entropy as a human readable string, which is a mnemonic. It can be from 12 to 24 words in 8 different languages. And then from that, you can deterministically derive a tree structure of different key pairs. It's incredibly powerful. And this is the industry standard. We absolutely suggest using this. And you can also use XPub wallets. And extended file is like the root of a branch in the tree structure of an HD wallet. And of course, extended public keys can only create branches of public keys, but there's also xpriv or extended private keys as well. One of the reasons for Avalanche's meteoric rise in the last year has been our C chain being 100% backwards compatible with existing EVM developer tooling and workflows. So devs really just need to add Avalanche as a new network for their existing workflow, and things just work. And so you can see here, I have listed Open Zeppelin, Truffle, Hard Hat, Remix, MetaMask, the list goes on and on. If your existing EVM workflow will work on Avalanche, you simply need to add Avalanche's network. Here you can see I have the settings for the mainnet, Fuji, which is our test net, and then for a local, if you want to spin up a local network, you just plug those values into your existing tooling like MetaMask or Hard Hat or Truffle, and everything will just work out of the box. And so there's a huge opportunity over existing parts of EVM, other EVM ecosystems into the Avalanche ecosystem by simply forking a code, forking an open source repo, adding the Avalanche network settings, and then deploying the dApp or the smart contract onto Avalanche. We also have a smart contract quick start. The goal of the smart contract quick start is to lay out best practices regarding writing, testing, and deployment of smart contracts to Avalanche's C chain. And we prefer Hard Hat over Truffle. We use Hard Hat internally, although Truffle is amazing and they're an amazing team. So we built the smart contracts quick start using the development environment Hard Hat. And this gives you a basic workflow for writing, testing, and deploying smart contracts. And included are an ERC20 or a fungible token example. We also have an ERC721 or a non-fungible token. And both of those just extend the industry standard Open Zeppelin contracts. So Open Zeppelin is a great team who have a bunch of open source, peer-reviewed, and just battle-hardened smart contracts that you can extend using object-oriented inheritance. And so we've done that. And we also have a storage example that shows a very simple example of how to write and read a small value to and from the chain. So Avalanche, as you might know, or if you're not aware yet, Avalanche isn't just a single blockchain. It is a network of subnets and blockchains. And each subnet is ultimately going to be its own paradigm with a specific and unique tooling and companies and workflows and everything. So recently, we even had a new subnet launch called Spaces, which is an authenticated hierarchical key value store with EIP 712 compatibility, state expiry, and fee-based metering. And then there was also another one recently launched that was called WOGME. And so here's just some tooling that might be available. We have the Spaces VM, which I just mentioned. We also have AvaSim, which makes it easy for anyone to spin up a local instance of an Avalanche network to interact with the standard API or to test a custom VM. Subnet EVM is the virtual machine that defines the subnet contract chains. Subnet EVM is a simplified version of the Core V chain, and it implements the Ethereum virtual machine and supports Solidity smart contracts as well as most other Ethereum client functionality. And so, today there are many teams which are still launching their own L1 EVMs. We suggest that you should now do that on the Avalanche network, and you get all of the goodies that I'm telling you out of the box. And we have a virtual machine for that called the Subnet EVM. We also have the timestamp VM, which defines a blockchain that is a timestamp server. Each block in the blockchain contains this timestamp when it was created, along with a 32-byte piece of data that we call the payload. And each block's timestamp is after its parent's timestamp. And this is like a proof of existence server. So you may have heard of this in the past. If you have a document, you can take a hash of it, write it to the blockchain, and then later you can prove that you were the person who had that document by, again, taking a hash of it and comparing that hash with the hash which was written to the blockchain to prove proof of existence or ownership. We also have the Avalanche virtual machine, which is a DAG, a directed acyclic graph with partial ordering. And this is best suited for commutative transactions like peer-to-peer payments or simple token transfers. It's parallelizable, it's prunable. It is also UTXO based. It's extendable via feature extensions. So today there are 3 feature extensions. There's SecP 256K1 assets, there's non-fungible tokens, and then there are what are called properties, which allow you to tie a key value pair to an address. But you can imagine extending the AVM functionality by plugging in Schnorr signatures or BLS SIGs or post-quantum cryptography, that kind of thing. And then we also have tutorials for creating virtual machines and creating subnets. There is also a public API server, which allows developers to access the Avalanche network without having to run a node themselves. The public API server is actually several Avalanche Go nodes behind a load balancer to ensure high availability and high request throughput. And the public API server is at https api.avax.network for mainnet and https api.avax-test.network for testnet. And to access a particular API, you just append the relevant API endpoint. So for example, to send API calls to the X chain, it would be api.avox.network/ext/bc/x. We also have sticky sessions. So requests to a public API server are distributed by load balancer to an individual node. And as a result, consecutive requests may go to different nodes, and this can cause issues for some use cases. So for example, one node may think a given transaction is accepted, while for another node, the transaction is still processing. And to work around this, you can use sticky sessions, which are available both at the RPC public API node or with Avalanche JS. And this allows consecutive API calls to be routed to the same node. And usage of public API nodes is free and available to everyone without any authentication or authorization. Rate limiting is present, but many of the API calls are cached and the rate limits are quite high. So if your application is actually running up against a rate limit, please reach out to myself or somebody from our team and we can work something out with you. Next, we have faucets. So as a developer, you will need funds to test your dApp on the Fuji testnet. And to get funds, we have a faucet, which gives a drip of AVAX on the X or the C chain as requested. Drops are limited to one request per hour. So make the most of each drop so that you don't get rate limited. And again, if you find yourself needing larger amounts of Fuji AVAX that are practical to get from the AVAX via a drip, then please feel free to reach out to myself or somebody from the team. And again, we can work out something for you. Remember, these AVAX are on the Fuji testnet or on a local network, and there is absolutely no monetary value to these. And we also have a web wallet. So a critical part of any user experience in crypto is, of course, a wallet. It lets you store, send, and receive tokens and interact with smart contracts. And our web wallet is extremely high quality and it's open source. It lets you send on the X or C chain. You can earn by staking your tokens. It enables cross-chain swapping for moving AVAX between the XP and the C chains. And there is even an NFT studio for creating non-fungible tokens. You can manage your HD keys, so you can actually see past, present, and future derived addresses. And you can even sign a message with a private key to prove ownership over an address. And an Explorer is another critical part of the crypto user experience, and it enables you to drill down and see the historical and real-time data of the blockchain. And this includes blocks, transactions, addresses, and smart contracts. We have Snowtrace, which is an instance of the Etherscan created specifically for the Avalanche C chain, maintained by the Etherscan folks. And we also have our own Explorer, which is for the X and the P chain. And then there's even some third-party explorers, such as Avascan. They deserve a shout out. And then lastly, I just wanted to mention there is also funding in the ecosystem. So we have Avalanche X, which is a grant program for moonshots. We have Avalanche Rush, which is for incentivizing the blue chip dApps from other EVM ecosystems. And we have Blizzard, which is an ecosystem and infrastructure fund. So thank you very much. As I mentioned, my name is Gabriel Cardona. I'm developer evangelist from Ava Labs. You can reach out to me at CG Cardona on Twitter or Telegram. Thank you so much and best of luck for the hackathon. Cheers.
Okay, thanks, Gabriel. So thank you both, Gabriel and Dan. I know you two guys have been preparing a lot for this hackathon. So thank you for your help. So that's all for the second workshop. And I'm pretty sure you got a lot of interesting and even new stuff for you to digest. And if you have the capability of building something really interesting and cool, and if you got ideas, so do not wait there, but register your projects on our hackathon's application website. Let me share these application sites. Okay. Hold on. Okay. Cool. As you can see, this is the official application website. And we have up to now altogether 24 projects has been submitted already. Okay, let's find out what kind of these projects are. Oh, Silver Swap. I noticed you basically asked a lot of questions. Good work. Keep trying. And we have DeFi. We have Gamefi. Okay, this looks cool. and Metaverse, Metalands, all sorts of projects. So definitely we want to see more interesting projects coming shortly. And do remember, if you like these projects, vote for them using your AVAX token. And if you think your project or your idea is even cooler than this, okay, come on, beat them, submit now. Okay, but not in a hurry. As you can see, our deadline for this hackathon is 31st of March, which means we still got approximately 50 days left. So prepare carefully your project and your idea and present them to us. But I do suggest you should not only present the idea, but better with the code base link. So we judge will evaluate the project with different perspectives like tech, commercial, and implementation level. Okay, I think that's all for today, but do remember we have our the third workshop on the 16th of February, and we will invite new guest speakers, bringing some useful solutions and products that definitely will help you with your building on AVAX. Okay, thank you again, and good night. Bye.